So this was a very well put together session because I'm going to talk about a lot of the exact same things that people have already talked about and kind of put it into this context of a solar wind equivalent for supermassive accreting black holes. I'm sadly not going to talk about my truncated disks that Chris talked about, but if you want to see a real version of that movie you showed, ask me. Okay, so let's start really fast. Other Chris on Monday gave a nice overview of what the corona is. So these accreting supermassive black holes emit across the electromagnetic spectrum. So from, X-rays over here, which is what you see when you look in the X-ray sky, to the UV and optical, this big blue bump, to IR frequencies for these examples. And these are thought to come from the corona, the X-ray corona, and then this accretion disk, which is unfortunately partially absorbed, and then some cold dust. Now, the reason this X-ray corona is surprising is because if you talk about these standard models that convert this gravitational potential energy into thermal, like Stefan Boltzmann, like thermal T to the fourth heating, then you do not expect any emission in the X-rays. You expect this, UV or optical. And so this is a very large fraction, like 1 to 10% of the overall luminosity that's going to this thing that we don't really know where it's coming from. So this corona is a significant fraction of the energy budget. It can also potentially play a role in maybe launching jets, maybe producing neutrinos, things like that. And from timing studies, we're pretty sure that it's very close to the black hole. So on the order of 10 gravitational radii, where the event horizon is on the order of 1 or 2 gravitational radii. So people have already even showed this figure. So thank you for that, Fabio. I'm going to talk about the AGN corona also not just as an interesting astrophysically object, but from a plasma physics perspective as well. So if we think about, Chris talked a little bit about this coronal heating problem. One of the main ways that we think the corona is actually going to be powered is through magnetic fields, so like reconnection or turbulence. This is probably something like the solar corona. So this is a favorite cartoon, but it's an old idea of something like interchange reconnection, where you have the loops connecting to the accretion disk, and then they reconnect, very similar to what Fabio just showed. So what I'm going to do here is show just how strongly magnetized this corona needs to be. So if you take the X-ray luminosity that we get from one of these AGN, and you assume that that converts, some fraction of that converts into, you take the magnetic energy density in the corona, and you assume that some fraction of that converts into X-ray luminosity through these magnetic dissipation processes, you get this lower limit. This could be risky. I'm not going to bother. Lower limit on the magnetic field that's required to produce that X-ray luminosity. And this is actually a pretty high magnetic field for that close into the black hole. So the other characteristics of this, if you calculate things like thermalization timescales, which other Chris talked about a little bit, the protons and electrons are at 2 different temperatures. The ion magnetizations are somewhere around 0.1 to 1. And it can be collisionless if it's compact enough, basically. And all this leads us to think that maybe there could be non-thermal particles in the corona. So you might think, okay, can we probe these processes in the corona? Maybe there's some good way to try to figure out what's going on in the corona. So you might say, what if there's synchrotron emission from these coronas? And then that synchrotron emission should probably happen in the millimeter if you calculate the synchrotron frequency. So can we use millimeter emission to probe what's happening in the X-ray corona? Because that would be nice, like a multi-wavelength kind of view of this process. So this is the same plot I showed earlier, but extended to larger wavelengths. I liked Chris's plot as well, but I didn't want all the model stuff in it. So basically, to like 0th order in AGN, there's 2 different types for this. One, we think have like large-scale jets, and so you have a lot of synchrotron emission, again, in the radio to millimeter here, so it's like a radio loud AGN. But then there are some AGN, the vast majority actually, that don't show this synchrotron emission at these wavelengths. They don't have these large-scale jets, maybe they're smaller-scale jets, and these are radio quiet. And these AGN are very promising candidates to study this millimeter emission from the corona because you're not contaminated by all of the jet emission. So recently, there's, I think ALMA was mentioned in a session on Tuesday or something. It has very fine angular resolution in this frequency band. So if you look at these radioquiet-Aegean well, I say very close in, but on the order of like a parsec scale, so getting rid of all the stars and everything that's going around, you actually see an excess of millimeter emission above what you would expect from dust or star formation processes. And observational observers are very excited about this. They've been characterizing things like this component has a flat spectral slope, for example, which is very odd, as I'll get into. And the amount of energy that's contained in this component is about this millimeter to X-ray ratio is about 10 to the minus 5, 10 to the minus 4. So there's a lot of excitement about maybe we can use this component to tell us about what's happening in this magnetized plasma. I'm going to unfortunately be the bearer of bad news. So we're not going to be able to use it to probe that classical viewpoint of the corona as that very compact region of space. But it turns out to be wrong in a very interesting way that will lead me into talking about the solar wind aspect. So let's get into it. The main problem here is that if you take these very strong magnetic fields and you put them into this very small region of space, like that 10 Rg compact number, you're not optically thin anymore. And that optically thin frequency here, that's this kind of really useful number because you can probe this P, which is the underlying electron distribution function's power law index. So that would be really nice if you could, extract what that is for the corona. But you can't because the synchrotron photons start absorbing and thermalizing the plasma. In fact, if you take something like those magnetic fields I had put in before and you calculate where you start to self-absorb the photons, it's somewhere around 10 to the 13 hertz, whereas that millimeter emission is at 10 to the 11 hertz. So what that means is that you would be 2 orders of magnitude below this turnover frequency, and the slope of the spectrum drops off so quickly, you would totally wipe out any emission that you could potentially see from these coronal electrons. Unless you make an analogy to the solar corona and add in a solar wind component. So Stuart Bale showed this image in his talk, and I liked it so much that I stole it. But the idea here is that you have your accretion disk kind of anchoring the foot points of your magnetic field, and then there's turbulence and reconnection going on in this outflow here. And so the idea is like it's connected magnetically to this outflowing region that is rather analogous to the solar winds. This is also motivated by GRMHD simulations. So you can ask me about this. I have a little bit more plots here. But there's these outflows here in simulations of black holes without jets, basically. So if we take all of this and we take motivation from the GRMHD simulations, you can imagine as you move down the outflow, your magnetic field is decreasing, and so that turnover frequency that's killing off all of your emission is also moving down in frequency. And what this does is it allows you to add up to a flat spectrum instead of that nu to the 5 halves that kills all emission. This is very similar to an idea for radio jets, but this is a non-relativistic version of that. Maybe I shouldn't say that in a conference for relativistic plasmas. So now you can ask the question, okay, we have this turnover frequency as a function of height, so where does the millimeter emission actually come from? Well, so here is a plot of some examples of the turnover frequency, and as you move outwards from the black hole along the outflow, the turnover frequency is dropping, and that 100 gigahertz millimeter emission ends up coming from anywhere between 100 to about 10,000 gravitational radii, depending on your parameters. So this millimeter emission is probing this extension of the X-ray corona that is analogous to the solar winds. I'm going to skip this. And so now you can ask, okay, well, how does this model compare with some of the things that observers have been finding, right? And one of the key predictions of the observers is a very flat spectral slope, right? And so I showed that stacking up, but what actually is the slope? It turns out it depends on parameters such as how your magnetic field falls off, how your density falls off. But for an example, motivated by GRMHD simulations, that slope is 0. So it's totally flat, very similar to the Blanford-Koniggel. This is a plot of that. So observers care about how it depends on mass, for example. So I'm plotting that as mass. This gray region is kind of all the scatter of those observed spectral slopes. And you can see that the model here, right at 0, because it's, like I said, totally flat, is well within that kind of regime for what the observations have found, which is much higher than the synchrotron self-absorbed slope down here and the optically thin limit there. Also, that millimeter to X-ray luminosity ratio is kind of important. So what is that? And it turns out if you just calculate based on some of these fiducial parameters, it turns out that that ratio is dependent weakly on the ratio of the coronal electron magnetization to the mass of a black hole. And that's important because one of the observational characteristics was rough independence of this ratio on black hole mass. So that's this gray region here. And you can see if we, this is a first blush theory, we're very, very close to that number, which is very cool. So this solar wind outflow-esque sort of a thing coming from this corona seems to be a promising explanation for this new millimeter component of the AGN spectrum. And so a couple of things you might imagine doing in the future are like probing this corona and wind connection, so maybe like variability. You can measure variability of millimeter very easily. Well, not very easily, but you can. And that gives you size of your emitting structures. And so that could potentially tell you about probing how fast these structures are changing. And general magnetic field fluctuation timescale, which if you calculate for the millimeter emitting electrons is about a day, which is right, again, where observations have found this variability to be. One thing I want to highlight here from kind of a more plasma physics perspective is that these electrons are cooling very fast. They're in the fast cooling regime. So if they're losing most of their energy to radiation before they escape the system, so they're in the fast cooling regime. And so you can imagine there's some transition as you go further away where the cooling time becomes longer and you start to have electrons sticking around for longer. And it turns out that these 100 gigahertz emitting electrons are close to that boundary, and so they could be an interesting way to kind of probe this regime between fast and slow cooling. So with that, millimeter photons, you can't come from the X-ray corona, as in the typical swird of the X-ray corona, but if you have an extended outflow very similar to the solar wind, then it seems to be an interesting possibility for where this comes from. And I'm looking forward to studying how this dissipation process happens in more detail.
So you were talking about the separation of the millimeter observation for jets versus photons. And then you were like, observationally, it's not very feasible to track down without the wind. And then the wind that you added to the equation was kind of looking like similar to jet structure. So how could you observation, like for the sun, I understand it, you don't see the jet.
Right.
But observationally, those very small things that we observe, how can you dedicate, actually, is the separation still there? Like that's what you know about it, or like you know about the rotation of that black hole?
Separation as in jet versus outflow.
The AGN with the jet, but AGN without the jet, but with the wind.
Yeah. Yeah, this is a good point because like jet sort of thing and accretion disk winds are also very common, and this is neither of those, right? So kind of the idea, wait, this is probably good. So yeah, let's maybe start with a jet probably would be coming out more along the polar rotation axis of the black hole, and generally would be more relativistic, versus this flow would be more non-relativistic. That, I think, is probably one of the main differences. You actually probably would have this outflow in the presence of a jet. So when I looked briefly at a GRMHD simulation that had that was more strongly magnetized and had a jet, and I still found this sort of outflow region here. But the difference is just that observationally, because they're emitting sort of in the same regime, the jet synchrotron emission, which is from much larger scales, would kind of wipe out everything you might hope to see from closer in from the outflow. Yeah. Does that mostly answer your question? Or do you have more? Okay. Okay. Chris.
Nice talk. Your constraints against the corona seem to be largely based upon a uniform corona picture, where the plane is spread through, and you sort of put the outflow picture in. What's really doing is introducing a gradient in density and a gradient in the field that's giving you the stacking up.
Indeed, yes. That's why for a while I actually called this a corona.
So to what extent could you achieve the same thing with inhomogeneous corona?
Well, okay, that's an interesting question because, you know, you don't necessarily have to have a spherical corona. So people have modeled what I'm talking about with the millimeter as a spherical corona on the order of 1,000 gravitational radii. I think to more directly answer your question, so this this turnover frequency is where the optical depth to synchrotron self-absorption is 1, which depends, of course, on the path length through your medium. And then, as well as this, there's a magnetic field dependence. I don't think that if you restrained yourself to be within 10 gravitational radii, you can't get enough of a dropping off from the high magnetic fields to actually get the same effects as you would here. There's not enough space over the course of 10 RG. But yeah, so like what people usually do, this is still kind of an early field, so models are still coming out for this observationally. But what people usually do is they do exactly what you said, assume a spherical emitting region with a uniform magnetic field and then fit the size to it. And that's what I'm showing here. The blue is that uniform sphere, and the orange is my model with the gradient for like 1,000 RG. And you can see it's a difference in the magnetic field of like 2 or 3 orders of magnitude. And also it requires, like I said, that larger emitting region. And so these papers are arguing that the X-ray corona and millimeter corona are co-located, and they're 1,000 RG, which is like 2 orders of magnitude higher than the X-ray corona size. Exactly, exactly. So I'm not quite sure how they justified. I need to like talk to the people to see more what they were thinking, but that's kind of exactly why this gradient is more important. Yeah, I don't think this is working. I'm having trouble hearing.
This may be tapping into some of the things that you mentioned, just to reply to Chris's question.
Yeah.
So 2 things is if you can give a sense of the scale, like the sweeping of the frequency, or let's say the extent of the spectrum, what does it imply in terms of like the outer scale of the emission? And the second question, which is related to your sort of like variability discussion, whether you can distinguish this at this point from as a continuous flow, or versus like ejections of blobs that are intermittently sweeping the frequency from high to low.
Okay, so first question was the scale of the outflow, right? Yeah, so that's kind of what I was getting at with this plot is like how far out do you need to go before you start getting 100 gigahertz? And this is what depends on exactly what parameters you throw in. So for some canonical parameters, it's right around 1,000 gravitational radii away from the black hole. Yeah. There's actually an interesting part, though, because there was a microlensing event recently that constrained the millimeter emission to be coming from within 100 RG, according to what I just wrote down. And this model actually accounts for that as well. So what I've been talking about with all that stacking up was like looking at different heights along the jet. But you could imagine maybe looking down, because who knows what orientation this microlens thing is at. So if you look down this jet, because of the varying jet size, you have different path lengths down through the jet. And that actually will give you an appearance of the 100 gigahertz emission coming from way closer to the black hole, more like 10 to 100 gravitational radii. So the answer is probably anywhere from 10 to 10,000 RG, yeah. Second question was continuous flow versus ejection blobs, yeah. So that's the problem with these millimeter variability studies, right, is that they do literally how much do you change over what time, and then they assume that, you know, that is traveling at the speed of light, and so that gives you a constraint on the size of the emitting region, not the size of the total thing that's happening. Oops. So, yeah, I guess, I don't know, I haven't really thought about how being super clumpy, not just like within 10 RG, but further out would affect it, but I would assume it would kind of, you know, decrease your overall luminosity at that wavelength. So you could imagine like that ratio of millimeter to X-ray would probably change. Spectrum would probably, yeah, so like this stacking up thing here takes radiation from all different heights. It's mostly from one height, right? But it's a spread. So you might be able to track something like that. Yeah, exactly. They're essentially photospheres of different, different photosphere clumps, something like that. Yeah, that'd be a little bit more complicated, though.
All right. With this note,